All right, well, good morning, everyone. Thank you so much for joining us today for our bi-monthly research spotlight, which is part of the Minnesota Stormwater Seminar Series. My name is Maggie Karshnia, and I'll be your moderator for this morning. To start things off, I'm just going to give you a quick background on the research spotlights. Now, these spotlights are intended to highlight the results from the recently completed research projects that were funded through the Minnesota Stormwater Research Council and the Water Resources Center. These spotlights are paired with our every other month seminar series brought to us from St. Anthony Falls Laboratory in partnership with the Water Resources Center. The seminar series brings in nationally recognized stormwater experts to talk about key topics. If you haven't gone to one of these, you definitely want to check it out. You can learn more about these upcoming opportunities, whether they're the research spotlights or the seminar series, by visiting our website, which is listed in blue on the screen. And just in case you might have missed one or two in the past, a quick reminder that all of these past seminars and spotlights are available for viewing on the SAFL YouTube channel. So the link is in blue above. You can find these links also on the seminar website or through that link, or going to our main page on the Water Resources Center. And just a reminder too, to check out our website if you want to learn more about our current and completed stormwater research projects. You'll see the area circled in green on the screen. That's on our website. These are links to mid-project presentations, final reports, and more. If you want to learn more about what we're doing, this is a great place to do it. We're also in the process of updating our website, so you might see some more information available there as well coming up. Just a reminder too that we do have an annual meeting of the Minnesota Stormwater Research Council coming up on July 21st. If you'd like to learn more about the projects that are currently in process of being selected for the next round of funding, and you want the inside scoop on that, please join us. It'll be in person at St. Anthony Falls Laboratory. This is just a great opportunity to learn more about what this project is doing and the momentum it's gaining. And I'd also like to take a quick moment to thank our co-leads on this seminar series, Dr. John Gulliver and Dr. Andy Erickson, for all of their work and for all of the great support that SAFL's provided for the series since 2019. All right. And we do have some upcoming presentations coming up. So we have David McCarthy from Monash University Center for Water Sensitive Cities in Australia. So all the way across the globe, he's going to be coming to present on June 23rd, and he'll be talking about real-time monitoring and control of green infrastructure for improved stormwater management. Definitely don't want to miss that. And then, as I mentioned before, we do have that annual meeting of the Stormwater Council on July 21st. All right, so that brings us to today's research spotlight, which features a completed project funded by the Minnesota Stormwater Research Council and the Center's Stormwater Research Program. A quick note before we get started to please use the Zoom Q&A panel to submit and ask any of your questions. And if you like some of these questions and you really want to see it answered, be sure to give it a thumbs up. The more thumbs up a question gets, it'll rise to the top, and we're going to answer those first. There has been an occasion where we haven't gotten all questions, so if you really want to see something answered, be sure to give it that thumbs up. All right, and with that, I would like to introduce our presenters today, Daniel Furuta and Bruce Wilson. Daniel is a PhD student in the Department of Bioproducts and Biosystems Engineering at the University of Minnesota Twin Cities. His work is really focused on developing sensing systems and monitoring methods for air and water pollution, and on designing instrumentation for research and environmental sciences. And Bruce Wilson is a professor in the Department of Bioproducts and Biosystems Engineering as well. His research interest includes simulations of hydraulic systems and modeling uncertainty. All right, with that, welcome Daniel and Bruce.
Thank you. Thanks, Maggie, for the introduction and for all your work in putting this together. And thanks, Andy, for running it. I was having some technical difficulties today with my computer, so I'm calling in on the audio. I think we got it working, but if there's any glitches, I apologize, and please let me know. Yeah, so my name is Daniel. I'm a PhD student in Biosystems engineering here at University of Minnesota, Twin Cities. And this is a project I've been working on the last maybe year and a half. So I guess a little bit of background. As everyone here knows, it rains. And when it rains on surfaces like roads or parking lots or roofs or fields or whatever, that rain washes pollutants off of those surfaces. And that could be things like road salt or heavy metals or sediment or nutrients or whatever. And those pollutants eventually get into water bodies and cause problems. And so we need to monitor what's coming off in stormwater. And generally, as you all know, we do this by water sampling during stormwater events, during rain events. And the accuracy of this monitoring depends on the protocols and the methods that we're using to sample these stormwater events. And it's important that we have good accuracy, of course, because, people like y'all use this data to develop, regulatory frameworks or management practices or treatment options or the whole slew of things to try to mitigate these problems. So when we're looking at these methods that we use for sampling stormwater, there's a couple ways we can do it. We can do field studies, and this is a picture from a field study I helped on, where we go out and we either get real rain events or we put a rain simulator out on a mechanical rain simulator out on the surface we're looking at. We generate rain, we sample it, and then we see how the sampling did. Alternately, we can do a simulation, a numerical simulation in the computer, and try out different methods and see how they do that way. This has a few advantages. One advantage is it's much, much cheaper. Doing field studies, there's a lot of labor costs, there's equipment, there's permits and all of these things, analysis, for chemical analysis or whatever. While in the computer, you just have to build a model and run it, and costs are low. With numerical models, we can also isolate and examine different parameters, either of the pollutants or of the rain and the watershed. We can try to look at their impact on sampling accuracy. And in the field, the real world is very complex, and it's hard to isolate factors in this way. Another major advantage of simulation, numerical simulation, we can explore sampling methods and protocols that don't exist yet, either because no one's doing them, or because we don't have the equipment yet, or reasons like that. And so we can make modifications to methods, or we can come up with new methods, and we don't have the cost of actually having to build the machinery to do it. And so we can sort of predict what might be useful and then look at it in the field later and see if it actually works or not. So this project, our goal is to build an idealized, easy to interpret framework for simulating stormwater runoff. So this is purely in the computer, there's no field component of it. And then we're applying this framework to examining water sampling methods and trying to see if we can look at error sources and possible improvements and everything. So there have been a number of projects that have done similar work previously. Want to know more details, I have references in a slide at the end of this presentation. And they generally proceed in one of several ways. So some projects take real data that was collected at various sites during rain events, like the picture on the left. And they take this data and then they simulate sampling it in different ways. So it's real data, but the samplers that are being studied are in the computer. So you can try different samplers on this real data and see what your error is like. Another way that was maybe more popular in the 90s is they use real water data. So the rainfall data and the watershed response are real collected data. Then the pollutant behavior is generated by very simple mathematical relationships. Then there have been a few papers more recently that have used sort of full, very complex watershed models to simulate both rain events, the watershed response, and the pollutant wash-off. And they apply samplers within that framework. So we're trying to be somewhere in the middle of these different sort of complex, in this range of complexity. So we're trying to build a model that has straightforward parameters, idealized parameters that are relatively easy to interpret. We want our model to be simpler than the full watershed model, but complex enough to hopefully capture some real-world quirks in pollutant behavior. And we also want our simulation to be flexible enough that it can be applied to other problems with stormwater runoff, not just to water sampling problems. So this is the overall framework for our simulation. I'll talk about each component in more detail coming up. So what we do is we have a rain pattern. So this is the rainfall. We have a watershed response to a pulse. We convolve the two. That gives us our runoff hydrograph. We put that through our pollutant wash-off model. That gives us our pollutant concentrations. And then we put that through our virtual samplers. And we look at what we get. And again, I'll talk about each part of this in more detail. And also, so when I'm talking about the simulation framework, just due to the time allowed, I'm going to be going kind of fast. Don't worry if some of it's a little bit unclear, feel free to ask questions, but I think for our recommendations, which I'll get to later, it's okay if you just sort of have a sense of what we're doing. The details maybe we can fill in later if you want. And so we're looking at two main outputs from this framework. And if you do water monitoring, these should both be fairly familiar to you. These are sort of standard ways to represent pollutant concentrations. So the event mean concentration is sort of like it sounds, it's the average pollutant concentration through the runoff event. So we can just think of this as an average concentration. There is one important detail, which is that it's defined as a volume-weighted average pollutant concentration, not time-weighted. And the reason that this is useful is then we can take our event mean concentration, multiply it by the amount of water that came off in the storm, and that gives us the mass of pollutant that was washed off. And that's useful for regulatory purposes or whatever. The second value we're looking at is the peak value, and this is just simply the highest pollutant concentration that happened during the runoff event. These are the two main things that we're going to be looking at. So in our simulation framework, we are using tabular inputs for rainfall patterns. So, just a two-column table with time and rainfall at that time. And so there's a lot of different options for this in the literature. There's Huff curves, SCS, design storms, any real-world collected data. And then we take that and we scale the rainfall to the desired magnitude and duration that we want for that run of the simulation. So for all of the data I'm going to be showing in this presentation, we're using these rainfall patterns. These are the Huff curves for single point median rainfall events. If you're not familiar with these curves, this guy did this project in the 1950s in Illinois where he put out a network of, I think, like 400 rain gauges or something. And he collected a bunch of different data on rainfall storms, and then he tried to say, well, storms typically fall into one of these four categories. And then he put together these four curves, which are sort of like archetypal rainstorms. So these are often used as just typical rain events for simulations. They have a long history of use. And so if you look at them, you can see there's four curves. And the difference between them is just in what quarter of the storm does the rainfall peak happen. So the blue one, the first quarter storm there, you can see there's the rainfall peak right at the start. And in the red one, there's a peak right at the end. And in the other two, it's somewhere in the middle. So the idea is that these four patterns hopefully give a decent sort of range of rain events that approximate what happens in the real world. I should say that we did run the simulation with other patterns too. We tried SCS design storms, which you might be familiar with. We also did some patterns with more than one peak. We had a bimodal pattern. The results were a little different from what you'll see in this presentation, but our recommendations stayed the same. It didn't really change the overall results that we got from it. The next part of our framework is the watershed response. We're using another sort of tried and true method, the cascade of linear reservoirs, also known as the Nash model, after the scientists who came up with this, again in the 1950s. Details are probably not super important for now, but the thing to know is there's two parameters for our watershed response. Parameter n, which corresponds roughly to storage within the watershed, and then there's the parameter time to peak, is how long does it take for a pulse of water to get through the watershed. And the interaction between these two terms generates the curves that we're using for watershed response. The next part of our framework is the pollutant response. This is a little bit complicated looking, but basically what we're doing is we're saying pollutants, we're modeling pollutants as a combination of two types of behavior. So the first type, which is the term on the left there with the first arrow pointing to it, this is the exponential decay term, dependent on cumulative volume, the V in the in there. And this term is meant to represent pollutants that dissolve freely in stormwater and don't require force to wash off of a surface. So this might be something like chloride. So what you generally see with this is the concentration will be high at the start of the storm. It'll sort of drop over the course of the storm, and how sharp that decay is controlled by this parameter kappa in the X. The second term here, is the beta 3 and the Q and the beta 4, is meant to represent pollutants that require some force to detach them from the surface that the rain is hitting. So this might be something like sediment. It requires some amount of flow to wash off. If the flow is very gentle, it won't just dissolve and off the surface in the same way. And so the beta 3 and the beta 4 terms control the magnitude of this response and the sharpness of the sensitivity to flow. Then we have another term, which I'm calling blend here, which says how much of the behavior is the one term versus the other term. So one thing I should note here is we are not looking at real world pollutants in this framework. We're not looking at, for example, chloride or lead or anything like that. We're instead looking at these sort of idealized behaviors, the idea that we can look at what happens in this ideal situation and then make predictions for real pollutants based on other similarities to these idealized forms. This slide is maybe not super important, but I just want to say that we're deriving the terms from first flush behavior, the event mean concentration, and then a couple other parameters, and then we get the rest of it from optimization. I should say first flush, if you're not familiar with this concept, often in a runoff event, more of the pollution will come off in the early part of the storm than in the late part of the storm. And so our first flush parameter, FF25 in this case, is just a measure of that. So if we say FF25 is 50%, this means that 50% of the pollutant that came off the surface came off in the first 25% of the runoff volume. There's a decay in the pollutant wash off. So these are some example pollutographs that come out of the simulation. So what you can see is that, we're able to generate sort of a range of behaviors. Some of them have very sharp first flush behaviors, like in the bottom left, the orange one there has a very steep first flush. And some of them have much weaker first flushes, like the blue curves there. And then similarly, some of them depend more on flow, and some depend less on the flow. So we can get a range of pollutants from. And finally, the last part of our simulation is the samplers. So what kind of samplers are we looking at? We're trying to simulate machines like the one pictured here, which many of you might have used. So this is a machine with generally 24 bottles inside of it. And what it does is at certain intervals, which you program the machine to do, it'll pull a sample of water through a tube with a pump. It'll fill up one of those bottles and it'll move on to the next bottle. Then it'll fill that one, move on to the next one, keep going until they're all full. So that's what we're simulating in this framework. Frequently, these machines would have a flow sensor installed alongside of them. And we use that to measure the volume of runoff coming off as we're going. To get event mean concentrations, we do what's called compositing, which is we take our 24 bottles that got filled up with water, we pour them together into one bottle, and then we send that one off to the lab, and that's assumed to be the representative of the average concentration. And we're taking peak values as just the highest level in any of the samples we got. So which of the 24 bottles has the highest concentration, that's the peak. So we're looking at three types of, calling them standard water sampling methods. There's volume-based flow-weighted samplers, which means we take a sample at even volume intervals. So we have a flow sensor and we're measuring when this amount of water has gone by, take a sample. When this amount has gone by, take the next. And it's the same amount for every sample. And then we take the EMC by pouring all of the bottles together evenly, and we send that to the lab. We have time-paced, time-weighted sensors. That's where there's no flow sensor. So we say, for example, pull a water sample every 10 minutes and fill up one of the bottles. And then at the end, since we have no flow sensor, the only way we can make our composite is pour them together and send that to the lab. So our composite is time-weighted in this sense. And finally, we have a situation where we take a sample every 10 minutes or whatever, but we do have a flow sensor. So instead of pouring the bottles together evenly, we add them proportionally to how much of the volume of runoff that sample represents. And so we're calling this time-paced flow-weighted. And this is just a quick example. So you can see time-paced samplers take samples at even time intervals. Volume-paced is not even time intervals, but it's even volume intervals. Before I get into our results, I need to say something about our figures. So we've been going back and forth a little bit about the best way to represent our results, and we're still sort of thinking about it, but for now we're using plots like this. So our simulation framework, we're simulating many, many possible combinations of storms and pollutants, maybe like 600,000 combinations or something like that. And so what we're showing here is for all these combinations, for a given sampler type with this many bottles, here's the errors for all of those combinations. What we did not do yet is say which of these storm and pollutant combinations are most likely to occur in the real world. So we have not analyzed the frequency as it relates to the real world. So what that means is that we cannot necessarily say that the real world is likely to be close to the medians of these bars. It's possible that real world events will actually be at the extremes. We don't know yet. We haven't gotten into that yet. So when we're looking at these, don't just look at that sort of central shaded box area. Look at the whole size of the plot with the whiskers there. So our first result that fell out of this project, it's better to do volume-based sampling than time-based sampling, even if your flow sensor is pretty bad. So first, here is what happens if we're saying your flow sensor is perfect and your sampler is programmed to exactly the right size of the storm. You fill all your bottles every time and there's no water left over. There's no runoff after that. So the x-axis here is showing different number of bottles that get filled for these three types of samplers: time flow-weighted, time-paced, time-weighted, and volume-paced, volume-weighted. And then the y-axis is showing fractional event mean concentration error. So on the y-axis, if the error is 1, that means it's 100% wrong. The sampler thought that you had double the pollutant concentration you actually did. What we can see is that in general, the volume sampler is the way to go. Pretty straightforward. You know, if you add more bottles, you get better improvement. You don't really need to have a crazy number of bottles. If you have like 15 bottles or something, that's almost as good as if you have all 24 bottles. So if you have access to a flow sensor and in sort of ideal conditions, you always want to use volume-based sampling, never. And the same is true for peak concentrations here. So the difference is less dramatic. You know, the time-based sampler does almost as well for peak concentrations as the volume-based sampler does. But in general, if you have a flow sensor available, there's no reason you shouldn't just do volume-based sampling. It's to be better for everything in general. I'm gonna sort of just gloss over these 2 slides because there's kind of a lot going on, but we looked at the effects of different parameters on sampler performance. And what we found is that for time-based samplers, the rainfall pattern and the storm duration matter for accuracy. Whereas for volume-based sampler, it's mostly the sharpness of the first flush and how important that first flush behavior is that matters for accuracy. We can come back to this in the questions if anyone has more. So those figures I showed you were a situation where your flow sensor is perfect. There's no noise, there's no bias. Your sensed flow is exactly the real flow. And of course, in the real world, sensors are not perfect. So what we're looking at here is how bad can the flow sensor be and still be worth using. So we're representing flow sensor error as multiplicative bias. So on the x-axis there, 0.1, that means that the flow sensor is 10% high on its readings. So what we see is that even if the flow sensor is pretty garbage, even if it's 25% off, it's probably still better to use it than to just use time-based sampling. And so one thing this suggests is that it might be worth our time to focus on developing cheaper flow sensors, even if they're not very good. Because if we can afford to put a flow sensor out, and even if the performance is sort of mediocre, it'll probably still lead to better sampling than if we are just using time-based samplers. We also looked at sensor noise, so random error. And I'm not showing the plot here because it doesn't really have much effect on the performance, it turns out. And then the next source of error we looked at is what if the weather forecast is wrong? So what we were looking at previously, we were saying that you programmed your sampler exactly for the amount of runoff that you would see. But in the real world, of course, that's rarely the case. And generally, your sampler will either run out of bottles early, or you have some empty bottles at the end of the storm that didn't get filled up because your prediction of the storm size is incorrect because the weather forecasts aren't perfect. So on the right side of this plot here, the part that's not boxed, you can see that if you didn't fill all your bottles, so if you thought the storm was going to be bigger than it actually was, the volume-based sampler is still the way to go. It still outperforms the other options in general. But on the left side, which is where you run out of bottles, or you thought the storm was going to be smaller than it actually was, see, that's a big problem for the volume-based sampler. And actually, its performance at that point is not so good. The error magnitude is potentially very large, and it's not really doing better than the other sampler types. So what can we do about this? So our second recommendation is specifically in this case where you ran out of bottles with your sampler. So you thought the storm was going to be smaller than it was, and you weren't able to sample the whole thing you ran out. So our recommendation is that you do an unequal composite in this case to fix this problem with volume-based sampling. I'm going to skip that. So here's a little diagram showing what happens if you ran out of bottles. So on the top graph, there's 3 volume-based samplers. The top one is programmed correctly for the right amount of water that came off in the event. The middle is programmed for half, so it ran out of bottles halfway through the storm. The bottom one ran out of bottles 1/10 of the way through the storm. And so what we can see, and so what these arrows are showing, the green and the purple arrow there, if we ran out of bottles, the final part of the storm is not represented in our sampling. So those arrows are showing the last point where we have a sample collected. What you can see is everything to the right of that, we don't have anything representing it. So what we can do in that case is if we add more of the final bottle collected to the composite than the other bottles, as long as the pollutant concentration in the last part of the storm is closest to the final bottle, this will improve the accuracy. So looking at this in this middle case, the 50% forecast case, what we would do is we take that last bottle, pour that into the composite, and that's half of our composite. And then we make up the rest of the composite with the other bottles evenly. Or in this 10% case, the bottom one there with the purple arrow, which is pretty dire, the final bottle should be 9/10 of the composite and the other bottles are the remainder. So what we see is that this does improve accuracy in general. So the orange one is just a normal volume-based sampler where the composite is even. All the bottles are represented evenly. And the blue bars are where we do this uneven compositing method where we pour in more of the last bottle to make up for this missing the last form. And so what we see is that especially if the forecast is, if we didn't miss it by too much, this can help substantially, it seems like. So, if we only got the first 1/10 of the storm in this 10% case here, it's probably not much you can do. You're just out of luck. But if you got the first half of the storm, then doing this uneven compositing method, can potentially reduce your errors quite a bit. So depending on your pollutant and your situation, this is something maybe to look at. Of course, it's probably best not to run out of bottles at all. But if you do, this is sort of easy. You can do it in the field. It doesn't cost anything. And, potentially it's a way to salvage some results. So our final recommendation is looking at the other situation. So what happens if you didn't fill up all your bottles? So you thought that the storm was going to be bigger than it actually was, and you only filled some of the bottles in your sampler. In this case, we're proposing that front-loaded sampling might lead to generally better performance. So we're calling this the UMN algorithm, the University of Minnesota algorithm. So the idea here is that at the start of the storm, your volume intervals are fairly small. So you fill up a lot of bottles at the start of the storm, and then you fill the remainder of the bottles sort of more slowly toward the end of the storm. So we're over-representing the first part of the storm and under-representing the last part of the storm. And the advantage of this is then if the storm is much smaller than we programmed the sampler for, we'll have more bottles filled because we filled more early. And so we have a full algorithm to do this. If you're curious, you can read about it in our report for this project. I'm not going to get into the details too much, but the pacing in this algorithm is controlled by a parameter p. And graphically, this is what it looks like. So on the top left plot here, the orange dots are just the standard equal volume sampler like I've been talking about so far. And the blue dots are this new University of Minnesota front-loaded algorithm. So what you can see is that we fill most of our bottles very early in the early part of the storm, and then not so much in the later part of the storm. And you can see on the lower right that this parameter p lets us control how severe this front loading is. So if we have a large value of p, we really fill all our bottles early. We don't have many in the rest of the storm. If our parameter P is lower, then we fill a bit more bottles early, but it's relatively even. Then to do our event mean concentration, we add our bottles to the composite proportional to how much volume they represent, so it's uneven. So this plot's a little bit busy. So what's going on is this is showing for, okay, so the blue bars here are for a normal evenly spaced volume sampler, the standard one that I've been talking about previously. The other bars are showing this new algorithm, the front-loaded algorithm for different values of P. And just once again, if P is larger, that means we're filling our bottles earlier in the storm. If P is smaller, it's closer to being evenly spaced. So what you can see is that essentially we're trading off accuracy in good forecast for better performance in a worse forecast. So if the forecast is accurate at the 100%, this algorithm doesn't really have an advantage. The results tend to be biased, it looks like a bit, and it's probably best to just go for evenly spaced sampling. However, if you are regularly not filling all of your bottles, and you have your sampler programmed generally for much bigger storms than happens, and maybe this is the case because you aren't reprogramming your sampler before each event, and you don't want to run out of bottles or something like that. So in that case, this method might give substantially better performance at the cost of worse performance if you end up hitting the correct storm forecast. So this is for event mean concentrations. For peak concentrations, the difference is more pronounced, and actually the algorithm might be the way to go, even if your forecasts are somewhat accurate. The reason for this is that many pollutants tend to have a first flush effect. The peak concentration will often come early in the storm relative to the amount of volume. So this method is more likely to catch that because we're taking more bottles early in the storm. Yeah, so I guess to sort of sum up, we had kind of three main findings. So volume-based sampling is better than time-based sampling, even if your flow sensor is pretty bad. If you ran out of bottles because you were anticipating a smaller storm than you got, add proportionally more of the final bottles to your composite, and that'll often help your results, help your accuracy. And finally, if you don't reprogram your samplers, or if you generally are not filling all of your bottles, you might want to think about a front-loaded sampling approach like the one that we showed, especially if you're interested in peak concentration. I should say that we have tried this algorithm in the field. It's a little bit tricky to implement with standard water samplers, but it is possible. And you know, if anyone wants to know more about that, we can talk about that later. So our simulation has some pretty important limitations I want to bring up. So one is that rainfall patterns, we did not attempt to evaluate real-world frequencies. So like I said, we can't say that, you know, on average, your results will be like this. We can just sort of say for the combinations we tried, here's what tends to happen. Our watershed model is simple and doesn't account for, you know, for example, infiltration in the watershed or of storage and that sort of thing. And our pollutant model is also heavily simplified intentionally because we want the parameters to be easy to interpret. And because of that, it does miss some processes that probably affect things in the real world. So the next steps, like I mentioned, we need cheaper flow sensors. And we're also curious to what extent can we improve performance by adding relatively inexpensive electrical sensors, for example, turbidity or conductivity. Can we combine this with our sampling to get better accuracy? These are both projects that I have been working on with Bruce Wilson a bit, and you know, hopefully we'll have something to show eventually for these things. But for any engineers who are looking for sort of things to improve, we think these might be two key areas that are both fairly feasible and could have a fairly big effect on monitoring accuracy. Then the other thing is, like I mentioned, this framework we built is fairly general, and we think it could be applied for other applications. For example, testing management practices, looking at treatment options, or whatever else. And so hopefully, now that we have this framework, this is something that can be used to look at some other things beyond just sampling. And then finally, I'm currently working on a self-contained program you can use to plug in values for an event, and it'll spit out our estimate for error. I'm hoping to have this done pretty soon. So there will be a link at the Stormwater Research Program website at this address once it's done, and I'm hoping that'll be in June if everything goes well. And yeah, also we're working on refining this project, tidying up the results a bit and looking at a couple other things, and then we're hoping to write it up into a paper and publish it along with our full simulation framework. Hopefully sometime this year. I guess we'll see how that goes too. That is all from me. Be happy to answer any questions. I think Bruce is here too. If you have, will be chat.
Well, thank you, Daniel, for that great presentation of the research results. We do have some questions coming in. A quick reminder to everyone that if you do have questions, please submit them now in the Q&A section at the bottom of your screen. And don't forget to give a thumbs up to those questions that you want to see answered. We're going to be answering the ones with the most thumbs up first. Hopefully we'll have a chance to get to them all. So Daniel and Bruce, the first question I have for you is, ISCO samplers only have 24 bottles. Do you recommend multiplexing flow-paced auto samplers? We use 4 samplers per bottle, giving us 96 samples per storm.
Yes, that's a good question. I think, if your forecasts are pretty good and you're generally, filling all your bottles and you're not running out of bottles, 24 bottles is enough, I think, for a standard flow-paced sampler. But the big advantage of having more bottles is that then you can program it for longer storms, so it's likely that you won't ever run out of bottles. So I think in that case it could be very useful. I think if it's, I think the question, how many bottles do you need to get a good estimate of EMCs? I suspect 24 is fine. But I think in terms of making sure that you're capturing the full storm, even if it's bigger than you think, multiplexing like that, it definitely seems to me like it's useful. I don't know if Bruce, if you have any thoughts there.
Most of our work was done using relatively small watersheds. So I think I agree with Daniel on your comments on smaller watersheds. But if you're working with very large watersheds, then I would have to think a little bit more about the variability of those flow rates for large watersheds. So I agree with Daniel's general comments. There might be some exceptions if you have very large watersheds or complicated systems that we didn't look at.
Okay. So our next question is, what new flow sensing technology is good enough that you're thinking of?
Yeah, so I know Brian, actually, we've worked on this previously. I think that 2018 project. So Bruce and I have been looking at systems inside of storm drains, something that'll sit in there and catch the water flowing in, and then use a type of weir to translate flow into depth. We still think that's promising, even though there are some challenges with it. Obviously now flow sensors that people use are often like Doppler, and those are great, but I think it is a little hard to do those cheaply. So we've kind of been looking at a bit of a back to basics, old-fashioned weir type setup is something that could be cheaper. And there are challenges with it, of course, but I think due to the potentially very low cost, it's worth investigating.
Great, thanks. Next question is, how does one know if they are at the 20% of the total storm or the 50% of the total storm?
Yeah, good question. So if you have a flow sensor, you're recording the flow data for the whole storm, and accordingly, you can use that data to see when your last sample came. If you don't have a flow sensor, you don't know, and you're out of luck, I think.
All right, next question is, the UMN weighting seemed to perform best with a p-value of 2 to 3, both for EMC and peak values. Any ideas why this was the case?
Yeah, so that's here. So so if you look at this, what value of P, the best performing value of P depends on how badly you missed the mark, if that makes sense. So for example, if the forecast was way bigger than your storm event, you want a higher value of P. If your forecast is generally pretty accurate and you're maybe just missing it by a bit each time, you want a smaller value of P, which is closer to the equally spaced volume sampler. So I think the way to decide what value of P you need is sort of within that trade-off. Is your priority making sure that you get okay results even if your forecast is way wrong, or is it trying to get the best results if your forecast is relatively good? And I think the optimal value of P would probably depend on the site and the pollutant you're looking at. I haven't gotten to the point where I can answer that very exactly, but it's going to trade off, I think. Bruce, I don't know if you have some more about that one.
I think it's also dependent on the type of runoff response you're anticipating. So if you're anticipating a first flush and a relatively large storm, then you'll want to catch those peak concentrations. And in that case, you'll want a larger P values as well. So, but if you're interested in the event mean concentrations, then even for a larger storm, you're probably interested in shifting down to a smaller P value. So, I would say a P between 1 and 3 would be sort of a reasonable way to go. And a P near 1 would be if you are interested in capturing the peak concentration for a major error in forecasting, and go for a 3 if your focus is more on the event mean concentration.
Great, thanks. Next question is, how does this information apply to single bottle large composite sampler? It seems like we should take a lot of small subsamples and then try to collect all of the storm in a single bottle.
Yeah, so that approach is called microsampling, and there's been a number of previous studies that have looked at that. And microsampling in general is a good way to go. So volume-based microsampling generally will give you the best performance, where you take a whole bunch of different samples and they're poured into one bottle. One problem with that is that you can't estimate peaks. You only have one result that comes out of it. So, if you're just looking at EMCs, I think that, a sampler is the way to go. You also want peak information. I think that's probably not as useful. Again, I think it's sort of a trade-off in what you're looking at, but yeah, in general, that microsampling will be a good way to go. One thing though is we did find that with volume-based sampling, you don't necessarily need a huge number of samples to get pretty good results. It kind of flattens out pretty quickly. So I think a machine like that is definitely a good option, but I think you can still get good results with a discrete samples like in this system we're talking.
I have heard some practitioners complain about just the logistics of setting up the instrumentation to grab many small samples. So another issue just might be the logistics of how to collect small samples, the collection tube and pumping the water through and stopping and starting. And I've been told that there's some logistics with setting up systems in the field.
All right, next question is, have you given some thought to using sampling data to come up with better event mean concentrations? Thinking of something like TP, where there are substantial dissolved plus particulate components. I know there are not a lot of event subsampling bottle data out there, but it would be interesting to see how those fit into that blended model.
Yeah, so Ben, I think I'm assuming you're asking about have we thought about using like real world events to sort of inform our parameters in our simulation framework, I think. Assuming that's your question, the answer is yes. And I think actually Bruce is going to talk to you and Jacques about doing that next week.
Yeah, we are a part of our goal is to do some analysis of data, and Ben, data that you have looks pretty tempting to us. So we'll be talking to you about that.
Great. Okay, next question is, if you have a sampling device failure, like battery runs out, tube disconnects, can this simulation be used to estimate the EMC or peak from a partial sample?
You know, I'd have to think about this a little bit. My sort of intuition is that this would be similar to where your forecast is wrong, except you don't have flow data from the later part of the storm. So I think it would be similar to that case, except probably worse. This is certainly something we could build into the simulation fairly easily. Yeah, that's certainly something we could look at in the future. Like I said, you know, in this, oh, sorry, go on.
I was just going to say, I agree with Daniel. I see it is similar to the case where we just sort of run out of bottles. So you maybe we're going to collect 24 bottles, but because of a breakage or some equipment failure, you only have 12 bottles. As long as you still have reliable flow measurements, then you could take the last bottle that you have. That's a good estimate, or hopefully is reliable, and use it to make an estimate of what the event mean concentration might be, following the procedures that Daniel talked about in the seminar.
I think if your flow sensor breaks, then maybe, you know, you're in trouble.
All right, next question is, could a similar approach be used to guide the sampling of stormwater ponds, which have prolonged outflows multiple days following storm events?
You know, that's a good question. Bruce probably will have some better insight into this than I do. I'm not certain how well our watershed model will work for that type of situation. But, you know, we could slot in a different watershed model, then sure. So I think possibly our framework, I'm not exactly sure, but I think something similar, yes, I would think.
My general thought is that the ponds probably have a less flashy response, and then the need to capture those more erratic kind of response you get in the inflow into the pond. So I think the methodology would work quite well in general for the pond. It probably work better. We'll have smaller errors if we use a methodology for the stormwater ponds than we would from the watershed runoff response.
All right, next question is, are you assuming 100% sampler efficiency? How would your conclusions change if you assume some inefficiencies, such as not capturing 100% of the sediment? Is this a fairly common occurrence?
Yeah, that's a great question. So for this, for the data here, we were assuming the sampler is 100% efficient, and we were also assuming that your chemical analysis is perfect. So we're assuming your lab work is perfect. We can certainly model both of those things, but we haven't yet. I'm not exactly sure how our conclusions will change. I guess they might be similar, but I think we will have to look at that probably before I could say very confidently about it. Bruce, maybe you have some insight into that.
I think it's a challenge if you know if your sampler is unable to capture all the sediment, for example, because it's deposited, and I think it's really sort of outside the scope of what we can do with our simulation code. I guess we could probably add an efficiency factor, but I think we'd have to think about some alternative ways of trying to address that issue.
That certainly is an important issue. I know in our past field experiments into this type of thing, we have found that for sediment, a lot of it doesn't make it into the sampler, it seems like.
So I think it's a really substantial problem that in our stormwater monitoring program across the entire state, or maybe across the entire country, of how to deal with the inefficient samplers. And I also agree it's a very good question.
Great. Our next question is, do you recommend pointing the sampler intake strainer upstream? The EPA Stormwater Manual recommends that the strainer is usually installed so that it faces upstream into the flow. This configuration minimizes the development of local turbulence that could affect representative sampling of constituents in the particulate phase.
I think, unfortunately, I gotta say I have no idea. I don't know, Bruce, if you have a.
Our experience has been we've tried different methods, and I'm not comfortable. I don't feel very strongly about any of our methods, actually. So given the type of storm that we have, some of the methods work well. We've had issues about plastic and other sorts of things getting caught in our collecting systems, and the role of that plays. It's hard for me to project what to do about that. So I guess the bottom line is I'm not sure what to do. I think once again, it falls in this efficiency collection of data, and I think it's certainly an important area of additional research.
Well, great. Well, I think we're just about wrapped up with questions. I'm going to try to squeeze in this last one, though. I can hear our state climate specialist communicating about now that we're here in Minnesota, we are here and we will in the future receive more severe storms and frequency, at least in certain parts of the state. So it seems from your work and modeling that automatic sampling sites could run out of bottles if not reprogrammed for these storms. Do you think that this work could help customize monitoring across the state or other areas based on climate precipitation forecasts?
You know, I'd have to think about that more, I think, before giving a very good answer. I think certainly what we found does highlight that it's important to keep on track with changing storm patterns. Because, if your sampler is regularly missing the forecast, that is a big problem, as we can. So, yeah, I think that's a really interesting question, and I'd have to think more about it. About how this would sort of tie into that.
I think the framework that we have set up if we get reliable estimates of what the precipitation depth will be in the future, we'll be able to simulate it within our framework. So I think the bigger issue is trying to estimate what the future depths will be. But if we have reliable estimates from our climate group or from other sources, then we could be able to put it into our simulation code and get you some answers.
Great. Well, that kind of concludes our time. I'm glad I was able to squeeze in that last question. So a virtual round of applause to Daniel and to Bruce. Thank you for sharing your work. And for all of our participants too, we're going to send all the questions to Daniel and Bruce for some additional follow-up. Andy will be sending that out with the answers shortly. I'm going to be placing a quick survey in the chat, which will also be sent in the follow-up email. Please take a few minutes to fill this out for us. It definitely helps us tailor future research spotlights to better meet your needs. Also, a quick reminder that our upcoming seminar series is happening on June 23rd. David McCarthy, all the way in Australia. And we hope that you can join us for that. But thank you guys all again. Thank you, Daniel. Thank you, Bruce. I hope you guys all have a great day. And I'm going to throw that survey into the chat right now. If you can click on that before you leave. All right. Thank you guys so much.